There's a place in the universe where temperatures plunge so low they defy comprehension, a frigid void where atoms almost stop moving entirely. And yet, against all logic, this icy abyss isn't dark. It burns with a ghostly glow, a light that shouldn't exist. This isn't science fiction. It's one of the cosmos' most baffling paradoxes, and it's happening right now in the deepest corners of space. What if I told you that the coldest places in the universe aren't just frozen wastelands? They're alive with quantum fire, a spectacle that rewrites everything we thought we knew about physics. This is the story of how emptiness shines. It's a tale woven from the bizarre rules of quantum mechanics, where particles vanish and reappear, where energy defies expectation, and where the vacuum of space itself crackles with hidden activity. Think about that for a moment, a place so cold it's barely above absolute zero, the temperature where all motion theoretically stops, and yet there's light. Not from stars, not from collisions or explosions, but from the sheer strangeness of reality itself. How does this happen? What force could possibly ignite brilliance in the ultimate freeze? That's the mystery we're diving into today, a journey to the edge of understanding where science meets the surreal. We'll uncover how quantum fluctuations turn nothingness into something, how the universe's coldest corners become canvases for radiant energy, and why this phenomenon might hold the key to secrets far beyond our current grasp. From the eerie glow of neutron stars to the mind-bending behavior of particles at near-zero temperatures, this isn't just a lesson in astrophysics. It's an invitation to witness the universe's most elegant contradictions. So buckle up. By the end of this, you'll never look at the night sky or the nature of reality the same way again. Absolute zero isn't just cold, it's the end of the thermometer, the point where even atoms surrender to stillness. At -273.15 degrees Celsius or 0 Kelvin, the concept of heat vanishes entirely, or at least that's what classical physics tells us. But the universe has a way of bending the rules. To understand how the coldest places in space can glow, we first have to grasp what happens when matter approaches this impossible chill. In labs on Earth, scientists use lasers and magnetic fields to strip atoms of their energy, slowing them down until they're barely moving. These experiments create temperatures just billionths of a degree above absolute zero, colder than the void between galaxies. And here's where things get weird. At these extremes, atoms stop behaving like individual particles and merge into a single quantum wave, a state called a Bose-Einstein condensate. Picture a crowd of people suddenly moving in perfect unison, as if they've become one entity. That's matter in this state, no longer solid, liquid, or gas, but something entirely new, governed by the surreal laws of quantum mechanics. This is the realm where particles teleport through barriers, where matter exists in two places at once, and where the vacuum itself isn't empty. Even in the deepest cold, quantum fluctuations spark tiny bursts of energy particles popping in and out of existence like cosmic fireflies. These aren't glitches, they're proof that emptiness is alive with activity, a seething quantum foam that defies our everyday intuition. Now, take this phenomenon to space. In the shadow of neutron stars or within vast molecular clouds, temperatures hover just above absolute zero. Yet these regions shimmer with faint light, not from stars, but from the same quantum dance we've recreated in labs. It's as if the universe is whispering a secret. Cold isn't the absence of energy. It's a stage for some of reality's most spectacular performances. The Boomerang Nebula is one of the strangest places in the cosmos, a frostbitten ghost of glowing gas where temperatures drop to just 1 degree above absolute zero. That makes it colder than even the background radiation left over from the Big Bang. And yet, this frozen expanse doesn't fade into darkness. It flickers with an eerie luminescence, a paradox that challenges our very definition of emptiness. How can light emerge from a place where heat itself seems impossible? The answer lies in the quantum realm, where the rules of physics twist into something extraordinary. At the heart of this mystery are quantum fluctuations, tiny, unpredictable ripples in the fabric of space-time. Even in a perfect vacuum where no matter or radiation exists, these fluctuations spark particles into existence for fleeting moments before they vanish again. They're called virtual particles, and though they last only fractions of a second, their effects are very real. Picture the void as a restless ocean, with waves constantly rising and collapsing. These waves aren't made of water, but of raw energy, and when they collide, they can release light. That's the glow we see in the Boomerang Nebula, not from stars or burning gas, but from the universe itself refusing to be truly empty. This phenomenon, known as quantum electrodynamics, reveals a startling truth. What we call nothing is anything but. The vacuum of space is a seething, dynamic arena where particles and antiparticles duel in an endless dance. Sometimes, these virtual particles borrow enough energy from the universe to briefly become real, emitting photons as they annihilate each other. In the extreme cold of the Boomerang Nebula, where atoms move sluggishly and heat is almost non-existent, these quantum fireworks become visible. It's as if the cold sharpens the contrast, making the faint glow impossible to ignore. But the implications go far beyond a single nebula. This quantum shimmer appears around neutron stars, in the vast stretches between galaxies, even in the empty pockets near black holes. Each of these environments shares one critical feature. They push matter and energy to their limits, revealing the hidden mechanics of reality. The colder the space, the more dominant these quantum effects become, turning the void into a canvas for the universe's most delicate light show. So the next time you gaze at the night sky, remember those dark patches aren't truly dark. They're alive with quantum energy, a silent symphony of particles flickering in and out of existence. The coldest places in the universe don't just defy our expectations, they rewrite them, proving that even in the deepest freeze, the cosmos finds a way to shine. The Boomerang Nebula isn't just another cloud of gas in the cosmos, it's a cosmic contradiction wrapped in frost. Stretching over 3 trillion kilometers, this hourglass-shaped nebula is the coldest natural place we've ever discovered, with temperatures plunging to a single degree above absolute zero. That's colder than the empty void between galaxies, colder even than the afterglow of the Big Bang itself. Yet, when Hubble turned its gaze toward this frozen expanse, it didn't find darkness. Instead, it captured a faint, haunting glow, a light with no obvious source. What makes this nebula so unnaturally cold? The answer lies in its dying star. Thousands of years ago, a red giant at its core began shedding its outer layers at breakneck speeds over 150 kilometers per second. This violent ejection created a cosmic wind so intense that it sucked heat from the surrounding gas like a celestial refrigerator. But here's the twist: as the gas expanded into space, it didn't just cool down. It became a laboratory for quantum weirdness, where the very absence of heat revealed something extraordinary. Telescopes like ALMA, designed to detect millimeter waves, peered deeper into the nebula's heart and found something unexpected. The gas isn't just cold, it's filled with intricate structures like ripples frozen in time. These aren't random patterns, they're the fingerprints of shockwaves, evidence of the dying star's turbulent final acts, and within these ripples, something even stranger happens. The extreme cold amplifies quantum effects, turning the nebula into a stage for virtual particles, those fleeting bursts of energy that defy classical physics. As these particles pop in and out of existence, they leave behind traces of light, a ghostly shimmer against the frigid backdrop. But the Boomerang Nebula's glow isn't just a curiosity. It's a clue. By studying this frozen enigma, scientists are unraveling how quantum mechanics operates in the most extreme environments. The nebula's light isn't powered by stars or collisions. It's the universe itself proving that emptiness is alive with possibility. Every photon emitted here tells a story of particles dancing on the edge of reality, where the rules we take for granted no longer apply. So while the Boomerang Nebula may hold the title of the universe's coldest natural place, it's anything but lifeless. It's a cosmic paradox, a place where the absence of heat reveals the universe's deepest secrets. And as telescopes grow more advanced, who knows what other contradictions we'll uncover in the frosty depths of space. One thing's certain, the colder the cosmos gets, the brighter its mysteries shine. Virtual particles are the universe's best-kept secret phantom actors in the quantum play, appearing and vanishing so fast they defy detection. Yet their fleeting existence leaves behind ripples of light in the darkest, coldest voids of space. To understand how this works, we need to step into the bizarre world of quantum field theory, where even empty space isn't truly empty. Picture the vacuum as a stormy sea, its surface constantly churning with waves of energy. These waves aren't just abstract concepts, they're particles and antiparticles flickering into being, borrowing energy from the universe for fractions of a second before disappearing again. It's like a cosmic loan shark scenario. Particles take out energy loans but must repay them almost instantly, annihilating each other in the process. But here's the catch, sometimes these virtual particles don't cancel each other out cleanly. Near the immense gravity of a neutron star or the crushing pressure of a black hole's event horizon, one particle might get dragged away before it can reunite with its counterpart. The energy debt goes unpaid, and what was once virtual becomes real, a burst of detectable light in the darkness. This is Hawking radiation in action, the same phenomenon that causes black holes to slowly evaporate. But it's not just extreme gravity that unlocks this quantum light show. In the frigid expanse of the Boomerang Nebula, where atoms move slower than glaciers, the absence of thermal noise makes these tiny quantum sparks visible. It's as if the cold turns up the contrast on reality's hidden layer. The math behind this is even stranger. According to Heisenberg's uncertainty principle, the more precisely you try to measure a particle's energy, the less you know about how long it exists. This loophole allows virtual particles to briefly violate energy conservation, popping up anywhere, even in perfect vacuum. Normally, their effects cancel out, but at the quantum scale, normally is a flexible term. When two uncharged metal plates are placed incredibly close together, in a vacuum, a setup called the Casimir Effect, virtual particles with longer wavelengths can't fit between them. The particles outside the plates outnumber those trapped inside, creating a measurable pressure that pushes the plates together. It's direct proof that these quantum fluctuations aren't just theoretical, they have tangible, observable consequences. Now imagine this on a cosmic scale. In the cold molecular clouds where stars are born, virtual particles interact with magnetic fields, producing faint radio waves. Around pulsars, their annihilation creates gamma-ray flashes. Even in the vast voids between galaxies, where temperatures hover just above absolute zero, these quantum sparks add up to a pervasive glow, light without stars, heat without fire. The colder the environment, the quieter the background noise, making these quantum whispers easier to detect. It's a reminder that the universe's most profound revelations often come not from its brightest objects, but from its darkest corners. What's truly mind-bending is that this quantum glow might hold clues to deeper mysteries. Some theories suggest virtual particles could be connected to dark energy, the unknown force accelerating the universe's expansion. Others propose they might help explain why the cosmos has more matter than antimatter. Every flicker of light from the void is a piece of a puzzle we're only beginning to assemble. So while virtual particles may be fleeting, their impact is anything but. They're the universe's way of reminding us that nothing, not even empty space, is ever truly at rest. Even in the deepest chill of space, where motion grinds almost to a halt, there's a hum of energy that never fades. This is zero-point energy, the universe's baseline, the irreducible buzz of existence itself. Think of it like a car engine idling at a stoplight. Even when it seems still, there's a vibration, a readiness beneath the surface. In quantum terms, it's the lowest energy state a system can reach. But here's the twist, it's not zero. Not even close. At the heart of this phenomenon lies Heisenberg's uncertainty principle, which tells us we can never pin down a particle's position and momentum with perfect precision. There's always a tiny wiggle room, a quantum jitter that keeps particles dancing even at absolute zero. This isn't just theoretical. In labs, scientists have observed atoms in ultra-cold traps still vibrating faintly, like a pendulum that never fully stops swinging. These residual fluctuations mean that true stillness is impossible, a revelation that turns the classical idea of nothingness on its head. Now scale this up to the cosmos. In the vast, near-empty regions between galaxies, where temperatures hover just above absolute zero, zero-point energy isn't just a quirk, it's a dominant force. It's why the vacuum of space isn't truly vacant. Instead, it crackles with this foundational energy, a sea of potential that occasionally erupts into visible light. Picture the surface of a frozen lake, seemingly motionless, but beneath the ice, currents still churn. That's the quantum vacuum, calm on the surface, frenetic beneath. This energy doesn't just linger, it interacts. When two uncharged metal plates are placed nanometers apart in a vacuum, zero-point energy creates a measurable force between them, pushing them together. This Casimir effect is like an invisible hand, proving that the empty space between objects is anything but. And in the Boomerang Nebula, where atoms are too cold to emit thermal radiation, zero-point energy's subtle nudges can excite molecules just enough to release photons, contributing to that eerie glow. But the implications go deeper. Some theories suggest zero-point energy could be the key to dark energy, the mysterious force accelerating the universe's expansion. If the quantum vacuum's energy density isn't perfectly balanced, and observations hint it isn't, it might be driving galaxies apart. Others speculate it could unlock revolutionary technologies like theoretical warp drives that harness this energy for propulsion. While these ideas border on science fiction today, they underscore a profound truth. The universe's coldest, emptiest corners are anything but lifeless. They're vibrant with hidden activity, a reminder that existence, even at its quietest, is never truly silent. So the next time you hear about absolute zero, remember, it's not the end of the story. It's a threshold, a doorway into a world where energy defies expectation, and the void itself shimmers with possibility. Zero-point energy isn't just a footnote in quantum mechanics. It's the universe's way of whispering that there's always more beneath the surface. Quantum entanglement adds another layer of weirdness to the already baffling glow of deep space. Imagine two particles separated by light years, instantly mirroring each other's states, a phenomenon Einstein famously called spooky action at a distance. Now picture this cosmic telepathy playing out in the coldest regions of the universe, where temperatures hover just above absolute zero. Could these ghostly connections between particles be secretly fueling the mysterious light we observe? The answer might rewrite our understanding of how energy moves through the void. At the heart of this idea is a radical possibility. Entangled particles could act like invisible wires, transferring energy across vast distances without breaking the cosmic speed limit, the speed of light. Normally, energy transfer requires particles to bump into each other or radiate photons, but entanglement defies that logic. In frigid environments like the Boomerang Nebula, where atoms are too sparse for frequent collisions, this spooky link might become the dominant way energy gets around. Picture a frozen pond where skaters glide without touching, each movement perfectly synchronized with a partner on the opposite shore. That's entanglement in action, a silent, instantaneous dance that could explain why light emerges where conventional physics says it shouldn't. Experiments on Earth are already hinting at this possibility. In labs, scientists have entangled particles and watched as heat seemed to teleport between them, bypassing the space in between. It's as if the particles shared an invisible backchannel, a quantum hotline for energy, now scale that up to interstellar space, where entangled pairs could span entire nebulas. If one particle in a pair absorbs energy, say, from a distant cosmic ray, its entangled twin might release that energy as light, even if it's floating in a region too cold to glow on its own. This could turn entangled particles into cosmic relay stations, quietly redistributing energy across the darkest corners of the universe, but the implications go deeper. Some theorists speculate that entanglement might even influence the universe's large-scale structure. Galaxy clusters appear to be arranged in patterns that defy random chance, almost as if invisible threads connect them. Could these threads be quantum entanglements forged in the early universe, lingering like ancient spiderwebs? It's a wild idea, but not impossible. The colder and quieter the environment, the longer entanglement can persist, free from the disruptive noise of warmer, busier regions. In the near-perfect chill of deep space, these connections might survive for eons, subtly shaping how energy and light travels through the cosmos. Of course, proving this isn't easy. Detecting entanglement across interstellar distances is like trying to listen for a whisper in a hurricane. But next-generation telescopes, like the James Webb Space Telescope and future quantum sensors, might finally catch these quantum whispers in action. Already, astronomers are scouring cold molecular clouds for anomalies, unexpected photon emissions, or energy patterns that don't fit classical models. Every flicker of light from these frozen voids could be a clue, a signature of particles talking to each other faster than light should allow. So while entanglement remains one of quantum mechanics' most elusive mysteries, it might also be the key to unlocking the universe's coldest secrets. From the eerie glow of nebulas to the hidden architecture of the cosmos, these spooky connections remind us that the universe is far stranger and more interconnected than we ever imagined. And as we peer deeper into the frosty abyss, we're not just studying the cold, we're uncovering the invisible threads that stitch reality itself together. To recreate the deep freeze of space here on Earth, scientists have built machines that defy intuition, devices so precise they can strip atoms of their energy, slowing them until they're nearly motionless. These aren't ordinary refrigerators. They're quantum playgrounds where temperatures plunge to within billionths of a degree above absolute zero, colder than the void between galaxies. The secret lies in a dazzling combination of lasers and magnetic fields, a technique called laser cooling. Picture a swarm of hyperactive atoms racing around like bumper cars. Scientists hit them with precisely tuned laser beams, each photon acting like a tiny brake, stealing a bit of the atom's momentum. Over countless collisions, the atoms slow to a crawl, their temperature dropping precipitously. But the real magic happens when these ultra-cold atoms enter a state called a Bose-Einstein condensate. Here, individual particles lose their identities, merging into a single quantum wave that behaves as one entity. It's like an orchestra of atoms suddenly playing in perfect unison. This exotic matter, first created in labs in the 1990s, mirrors the bizarre conditions found in the Boomerang Nebula where quantum effects dominate and particles defy classical expectations. Researchers manipulate these condensates with magnetic traps, sculpting them into rings or droplets to study how quantum mechanics operates at cosmic scales. One breakthrough came when scientists noticed something unexpected. Even in these near-perfect frigid conditions, the condensates emitted faint bursts of light. Sound familiar? It's the same paradoxical glow observed in deep space where virtual particles flicker in the void. By recreating these conditions on Earth, physicists realized the nebula's eerie luminescence wasn't an anomaly. It was a universal quantum signature, visible only when thermal noise fades away. Recent experiments have gone further, using optical lattices crystals made of light to simulate the extreme cold near neutron stars. Atoms trapped in these laser grids behave like cosmic particles in slow motion, revealing how quantum fluctuations can generate heat even in apparent nothingness. Some labs have even mimicked the Casimir Effect, measuring the phantom forces between plates in a vacuum, proving that empty space pushes back when squeezed. These earthly replicas of cosmic cold do more than satisfy curiosity. They're testing grounds for theories about dark energy, quantum entanglement, and the fabric of spacetime itself. Every time scientists dial down the temperature in these machines, they're not just cooling atoms, they're turning up the contrast on the universe's deepest mysteries. And as these experiments grow more sophisticated, they blur the line between laboratory and cosmos, proving that the coldest places in existence, whether natural or human-made, are always hotbeds of quantum revelation. Dark energy, the universe's most elusive architect, is stretching space itself apart at an ever-increasing rate. Yet in the coldest corners of the cosmos, where quantum flickers defy the darkness, a tantalizing question lingers: could this mysterious force be secretly fueling the glow? The answer might lie in the chaotic dance between dark energy and the quantum vacuum, where emptiness crackles with hidden potential. First, consider the scale of the mystery. Dark energy makes up roughly 68% of the universe's total energy budget, yet we've never directly detected it. It's not a particle, not a wave, but a property of space itself, a repulsive force embedded in the fabric of reality. Now pair that with the quantum vacuum, where virtual particles erupt and vanish in a frenzy. At their core, both phenomena deal with the energy of nothingness. Dark energy stretches the void, while quantum fluctuations fill it with transient sparks. Could they be two sides of the same cosmic coin? Some theories suggest yes. Imagine dark energy as an invisible tide, subtly warping the quantum foam. In regions of extreme cold where thermal noise fades, this interaction might become visible. Like wind rippling the surface of a pond, dark energy could amplify quantum fluctuations, coaxing virtual particles into lasting slightly longer, just enough to emit detectable light. It's not unlike how gravity near a black hole pulls particle pairs apart, creating Hawking radiation. But here, instead of gravity, it's the expansion of space itself doing the pulling. The math gets even stranger. Quantum field theory predicts that dark energy's density should be astronomically higher than what we observe. This discrepancy, called the cosmological constant problem, hints that something, perhaps an unknown symmetry or cancellation effect, is suppressing dark energy's full force. Intriguingly, in ultra-cold environments, certain quantum effects become magnified. If dark energy interacts with these effects even weakly, it might leave fingerprints in the form of anomalous photon emissions. Telescopes have already spotted unexplained microwave glows in frigid interstellar clouds, patches of light with no clear source. Could these be dark energy whispering to the quantum world? One radical idea proposes that dark energy isn't uniform. Instead, it clusters subtly in cold, low-density regions, creating pockets where its influence is stronger. In these zones, quantum fluctuations might receive an extra nudge, like invisible hands stirring the vacuum. The resulting light would be faint but pervasive, a background hum woven into the fabric of space. This could explain why the Boomerang Nebula's glow doesn't match traditional models. It's not just quantum mechanics at work, but quantum mechanics tangoing with dark energy. Of course, proving this is a monumental challenge. Detecting dark energy's local effects requires instruments sensitive enough to distinguish its subtle pushes from other quantum noise. Future experiments like space-based interferometers or ultra-precise atomic clocks might finally spot these minute interactions. Until then, the cold, glowing depths of space remain a cosmic laboratory, offering clues to one of physics' greatest puzzles. What's certain is this: the universe's coldest places aren't just frozen relics. They're dynamic arenas where the biggest mysteries, dark energy, quantum physics, the nature of emptiness collide. And with every flicker of unexpected light, they remind us that the cosmos still holds secrets waiting to thaw. Quantum tunneling is one of the most mind-bending tricks the universe has up its sleeve, a particle slipping through an energy barrier like a ghost walking through walls. In everyday life, this would be impossible. Throw a ball at a brick wall and it bounces back every time, but in the quantum realm, particles don't play by those rules. When temperatures plunge near absolute zero, atoms become sluggish and their wave-like nature takes center stage. This is where tunneling shines, literally. Imagine an electron trapped in an energy valley, like a marble at the bottom of a bowl. Normally, it wouldn't have the energy to climb out, but quantum mechanics grants it a bizarre escape route, a tiny chance to vanish from inside the bowl and reappear on the other side, as if the barrier wasn't even there. This isn't theoretical magic, it's measurable science. In labs, ultra-cold atoms regularly tunnel through barriers that should be impenetrable, a phenomenon harnessed in technologies like flash memory and scanning tunneling microscopes. But in the cosmic freezer of deep space, tunneling takes on a whole new role. When particles in frigid molecular clouds or near neutron stars encounter energy barriers, say, the magnetic fields around a pulsar, they don't always collide or bounce away. Some simply teleport through, carrying energy with them, and when these particles emerge on the other side, they can release that energy as photons, adding to the eerie glow of these cold regions. Here's the kicker: the colder the environment, the more pronounced tunneling becomes. At higher temperatures, particles jostle around too much, masking quantum effects. But in the near stillness of space's coldest voids, where thermal noise fades to a whisper, tunneling events stand out like fireworks in the dark. This could explain why telescopes detect faint light where classical physics predicts only darkness. The photons aren't coming from heat or chemical reactions, they're the aftermath of particles phasing through barriers that should, by all rights, stop them dead in their tracks. The implications stretch far beyond a few glowing nebulas. Tunneling might be a cosmic energy delivery system, shuttling particles, and their precious photons across regions too cold for conventional heat transfer. Picture a relay race where runners pass the baton not by hand, but by teleporting it forward, in the vast, sparse expanses between stars where atoms rarely collide. Tunneling could keep energy flowing where it's needed most. Some theories even suggest this process plays a role in star formation, helping particles bypass magnetic traps to coalesce into new stellar nurseries. Yet tunneling isn't just a cosmic oddity, it's a reminder of how deeply quantum mechanics is woven into reality. From the glow of distant nebulas to the chips in your smartphone, particles defy expectations, proving that the universe operates on rules far stranger than we once imagined. And as we peer deeper into the coldest corners of space, each flicker of unexpected light might just be another particle tunneling through the impossible, leaving behind a trail of quantum breadcrumbs for us to follow. Superfluidity is one of nature's most elegant magic tricks, a state where matter loses all friction and flows with impossible grace. Picture a liquid climbing the walls of its container, escaping through cracks too small for normal fluids, or swirling endlessly without slowing down. This isn't science fiction. It's what happens when certain materials like helium-4 are cooled to near absolute zero. But here's the twist. In the extreme cold of space, superfluidity might not just defy gravity, it could also defy darkness, emitting light through quantum sleight of hand. The key lies in how superfluids behave. At ultra-low temperatures, particles in a superfluid sync up into a single quantum state, moving as one coherent wave. There's no viscosity, no turbulence, just pure, uninterrupted flow. On Earth, we've seen this in labs where superfluid helium forms eerie, glass-smooth films that defy gravity. Now imagine this phenomenon playing out on a cosmic scale, inside neutron stars or drifting molecular clouds. Under these conditions, the superfluid isn't just frictionless, it's a playground for quantum effects that could generate light. One possibility involves vortices, tiny whirlpools that form in rotating superfluids. These aren't ordinary eddies. In a superfluid, vortices are quantized, meaning they can only spin at specific, discrete speeds. As these vortices interact, they can create ripples in the quantum field, releasing energy as photons. It's like dragging a spoon through honey, except the honey is a superfluid, and the spoon's motion sparks flashes of light. In the cold, sparse environments of space, where superfluids might exist in the cores of neutron stars or the depths of interstellar clouds, these quantum ripples could produce faint, ghostly glows. But there's another, even stranger way superfluids might light up the void. When a superfluid is stirred or disturbed, it can create quasi-particles, collective excitations that behave like particles, even though they're really just waves in the quantum soup. Some of these quasi-particles, like rotons or phonons, can carry energy away from the superfluid, and under the right conditions, that energy might escape as light. Think of it like plucking a guitar string. The vibrations don't stay trapped in the string forever. Some escape as sound. In a superfluid, the sound could be photons whispering out into the cosmos. The wildest part, we might already be seeing hints of this. Some neutron stars, the ultra-dense remnants of supernova explosions, emit puzzling X-ray and radio signals that don't quite fit traditional models. What if these signals are the fingerprints of superfluid cores, where quantum vortices or quasi-particles are shedding energy as light? It's a tantalizing idea, and one that telescopes like Chandra and Alma are actively exploring. Superfluidity reminds us that the coldest places in the universe aren't just frozen wastelands, they're laboratories for quantum marvels, where matter bends the rules and even the absence of friction can spark brilliance. Whether in the heart of a neutron star or the depths of a nebula, these exotic states of matter might be quietly painting the cosmos with light, one quantum ripple at a time. The Casimir effect sounds like something ripped from a sci-fi novel, an invisible force conjured from pure nothingness. Yet this quantum quirk is very real, and it might hold the key to why the coldest corners of space shimmer with unexpected light. Picture two uncharged metal plates placed nanometers apart in a perfect vacuum. Classical physics says nothing should happen, no forces, no interactions. But in reality, the plates snap together as if tugged by ghostly fingers. This is the Casimir effect in action, and its origins lie in the restless energy of empty space itself. At the quantum scale, the vacuum isn't empty, it's a seething foam of virtual particles flickering in and out of existence. These fleeting disturbances create waves of energy like ripples on a pond. Normally, these ripples cancel each other out, leaving no trace, but squeeze them between two plates and something extraordinary happens. Only certain wavelengths of virtual particles can fit in the narrow gap, while outside the plates, all wavelengths roam free. This imbalance creates a pressure differential, pushing the plates together with measurable force. It's as if the universe itself is allergic to true emptiness, filling every crevice with quantum whispers. Now, imagine this effect playing out in the frozen expanses of deep space. In regions like the Boomerang Nebula, where temperatures hover just above absolute zero, the Casimir effect isn't confined to lab experiments, it's a cosmic phenomenon. Dust grains, microscopic ice particles, or even the boundaries of molecular clouds could act like those metal plates, creating pockets where quantum fluctuations generate tiny bursts of energy. Over vast distances and timescales, these bursts could add up, releasing photons in a process that has nothing to do with heat or starlight. Instead, it's the vacuum itself flexing its quantum muscles. What's even wilder is how this connects to the light we observe. In cold, sparse environments, traditional energy sources are scarce, but the Casimir effect offers an alternative, a way for the universe to wring light from sheer nothingness. When those virtual particles between cosmic plates annihilate, they don't always vanish cleanly. Sometimes they leave behind a photon, a particle of light. In the near-perfect chill of interstellar space, where thermal noise is virtually non-existent, these faint emissions become detectable. It's not much, maybe a handful of photons per cubic kilometer over centuries, but in the vastness of the cosmos, that adds up to a glow science can't ignore. Recent observations back this up. Telescopes have spotted anomalous microwave emissions from cold molecular clouds, light that doesn't match any known chemical or thermal source. Some researchers suspect these signals could be the Casimir effect's fingerprints, virtual particles leaving their mark on the cosmos. Even more tantalizing, this quantum force might influence larger structures. In the dense magnetic fields around neutron stars, for example, Casimir-like pressures could nudge particles just enough to trigger light-producing collisions. It's a reminder that the universe's smallest phenomena often have the grandest consequences. So the next time you hear about the emptiness of space, think again. Between the stars in the coldest voids, there's a hidden push and pull, a quantum tension turning nothing into something. The Casimir effect isn't just a lab curiosity. It's a cosmic sculptor shaping light from the dark and proving once again that the universe's quietest corners are its most inventive. Empty space isn't empty, it's a quantum stage where particles perform spontaneous magic tricks. Under extreme conditions like those in the coldest reaches of space, the vacuum itself can conjure photons out of nothingness. This isn't a violation of physics, it's quantum field theory in action, revealing that what we call nothing is actually a bubbling cauldron of potential. At the heart of this phenomenon lies a radical idea. Fields permeate every inch of the universe, even in perfect vacuum. These fields aren't static. They vibrate with zero-point energy, constantly fluctuating like the surface of a restless ocean. Normally, these fluctuations cancel out, leaving no trace. But when space is stretched, squeezed, or cooled to extremes, the balance tips, and light emerges from the void. Take the dynamic Casimir effect as an example. In labs, scientists simulate cosmic conditions by vibrating mirrors at near-light speeds in a vacuum. This rapid motion distorts the quantum field, effectively kicking virtual particles into reality. Some escape as detectable photons, proving that motion alone can wring light from emptiness. Now imagine this on a cosmic scale. Near neutron stars, where gravity warps spacetime like a trampoline, or in the turbulent wakes of colliding black holes, space itself becomes a photon factory. The energy to create these particles doesn't come from matter. It's borrowed from the fabric of spacetime, paid back when the particles annihilate. Quantum field theory predicts this with eerie precision. According to its equations, every field has associated particles quanta that emerge when the field is excited. The electromagnetic field's quanta are photons, and in high-energy environments, they can appear spontaneously. But here's the twist: you don't always need high energy. In ultra-cold environments like the Boomerang Nebula, the absence of thermal noise makes quantum effects dominant. Virtual particle pairs, usually fleeting, can borrow energy from intense magnetic fields or spacetime curvature, becoming real just long enough to emit a photon before vanishing. It's as if the cold sharpens the universe's ability to see these quantum whispers. This process might explain more than just eerie nebula glows. Some astronomers suspect spontaneous photon creation plays a role in fast radio bursts, those mysterious, energetic pulses from distant galaxies. If spacetime itself can generate photons under the right conditions, it could rewrite how we interpret cosmic signals. Even the cosmic microwave background, the afterglow of the Big Bang, might carry fingerprints of vacuum photon production in its subtle irregularities. The implications stretch beyond astronomy. If we can harness vacuum fluctuations, technologies like quantum batteries or propulsion systems that tap into zero-point energy might leap from sci-fi to reality. Already, experiments with superconducting circuits show hints of extracting usable energy from quantum fields. The coldest places in space aren't just cosmic oddities, they're blueprints for a future where emptiness itself becomes a resource. Every photon born from the void is a reminder that the universe's most profound energies hide in plain sight, waiting for us to look closer. The cosmic microwave background is often called the universe's oldest glow, a faint whisper of light left over from the Big Bang, stretching across the entire sky like a ghostly blanket. This afterglow has cooled dramatically over billions of years, now registering at just 2.7 degrees above absolute zero. But in the coldest pockets of space, where temperatures dip even lower, something peculiar happens. The contrast between these frigid voids and the background glow creates a unique interplay, like a shadow cast against a dimly lit wall. And in that shadow, quantum effects take center stage, revealing connections we're only beginning to understand. Take the Boomerang Nebula, for example. At 1 degree Kelvin, it's colder than the cosmic microwave background itself. Normally, the background radiation would gently warm any object in space, however slightly. But in this nebula, the opposite occurs. It acts like a cosmic refrigerator, absorbing that ancient light and redistributing its energy in unexpected ways. Photons from the microwave background interact with the nebula's ultra-cold gas molecules, exciting them just enough to trigger secondary emissions. It's a bit like shining a flashlight through a prism. The light doesn't just pass through unchanged. It fractures, shifts, and sometimes amplifies, creating new wavelengths that wouldn't exist otherwise. This interaction isn't just a curiosity, it's a window into the universe's earliest moments. The cosmic microwave background carries imprints of the primordial cosmos, tiny fluctuations in density that seeded the galaxies we see today. When this light passes through regions like the Boomerang Nebula, those imprints can get subtly distorted, like a fingerprint smudged by cold glass. Astronomers call this the Sunyaev-Zeldovich effect, but in ultra-cold environments it behaves differently. Instead of scattering high-energy photons, the cold gas can absorb them, re-emitting the energy as faint radio waves or infrared light. These distortions aren't noise, they're clues. By studying them, scientists can map the distribution of matter in these frozen realms, uncovering hidden structures too faint to see directly. But the real surprise, some theorists suggest these ultra-cold regions might actually amplify certain features of the cosmic microwave background. In quantum physics, there's a phenomenon called stimulated emission, where incoming light prompts excited atoms to release identical photons, effectively boosting the signal. In the near-perfect chill of space's coldest voids, where atoms linger in delicate quantum states, the microwave background could trigger cascades of these emissions. The result would be patches of sky that glow slightly brighter than they should, like cosmic mirages forged by cold. This idea gains traction when you look at anomalies in microwave surveys. Telescopes like Planck have spotted unexplained bright spots in otherwise frigid regions, areas where the background light seems to flicker with extra intensity. One explanation is that these are cosmic magnifying glasses, where cold gas and quantum effects team up to bend and amplify the ancient light. If true, it would mean the coldest places in the universe aren't just passive observers of the cosmic microwave background. They're active participants, reshaping and even enhancing the oldest story the cosmos has to tell. So while the cosmic microwave background is often treated as a static backdrop, it's anything but. In the deep freeze of space, it becomes a dynamic player, interacting with quantum mechanics and extreme cold to reveal secrets about matter, energy, and the universe's hidden architecture. Every photon that passes through these icy labyrinths carries a message, one we're only now learning to decode. Black holes and the coldest voids of space might seem like opposites, one a crushing furnace of gravity, the other a frozen expanse of near-nothingness. But dive into the quantum undercurrents of both, and you'll find eerie similarities that rewrite our understanding of thermodynamics. At first glance, a black hole's event horizon and the Boomerang Nebula couldn't be more different. One pulls everything in, the other is so cold it pushes the limits of physics outward. Yet both are laboratories for quantum extremes, where the rules of classical physics unravel and light emerges from the least expected places. Take Hawking radiation, the faint glow predicted to escape black holes. Just as virtual particles flicker into existence in the frigid depths of space, they do the same near an event horizon. Here's the twist: when a particle-antiparticle pair pops up right at the edge of a black hole, one might fall in while the other escapes. From afar, it looks like the black hole is radiating energy, a process eerily similar to the quantum glow of cold nebulae. In both cases, what seems like empty space is actually a seething quantum soup, and the extreme environment, whether gravity or cold, amplifies effects we'd never see in milder conditions. But the parallels go deeper. Black holes obey laws of thermodynamics, with temperature and entropy just like any other object in the universe. A black hole's temperature depends on its mass. The smaller the hole, the hotter it glows. Supermassive black holes, like the one at the center of our galaxy, are downright chilly by comparison, with temperatures far below even the cosmic microwave background. This means some black holes exist in a state analogous to the coldest nebulae regions where quantum effects dominate because thermal noise is almost absent. In both scenarios, the lack of conventional heat doesn't mean stillness. It means quantum weirdness takes the spotlight. Then there's entropy. A black hole's entropy, a measure of disorder, is tied to the surface area of its event horizon, not its volume. This hints at something profound. Information might be encoded on the boundary, not the interior. Now consider a Bose-Einstein condensate in a lab or the quantum-synchronized atoms of a frigid nebula. In these ultra-cold states, particles lose their individuality and behave as a collective, their information smeared across the entire system. It's another strange echo. In both black holes and cold quantum systems, the rules of locality blur and the whole becomes something greater than the sum of its parts. The most tantalizing connection, both environments might be keys to unifying gravity and quantum mechanics. Black holes force these two frameworks to collide, exposing where they break down. Meanwhile, the quantum glow of cold space free from gravity's distortions offers a clean slate to study the same phenomena in isolation. By comparing these extremes, physicists are stitching together a tapestry that could explain everything from the birth of the universe to the fate of information swallowed by a singularity. So while black holes and cosmic ice might occupy opposite ends of the temperature spectrum, they are united by quantum rebellion. One burns with invisible fire, the other flickers with cold light, but both whisper the same truth. The universe's most dramatic stages are set where the ordinary laws of physics take a bow. Quantum decoherence is like a magician's trick gone wrong the moment the audience stops believing. The illusion collapses. In the quantum world, coherence means particles exist in multiple states at once, like a spinning coin mid-air. But when they interact with their environment, that delicate superposition shatters, forcing them to choose a single state. Now imagine this playing out in the coldest reaches of space, where temperatures near absolute zero should, in theory, preserve quantum states longer than anywhere else. Yet even here, decoherence creeps in, and when it does, it might just be the secret behind the universe's most unexpected light shows. The key lies in energy release. When a quantum system loses coherence, the energy it once used to maintain its fragile superposition doesn't just vanish. Like a stretched rubber band snapping back, that energy has to go somewhere. In the vacuum of space, it often escapes as photons, tiny bursts of light. This isn't just theoretical. Lab experiments with trapped ions and ultra-cold atoms have shown that controlled decoherence can produce measurable photon emissions. When scientists deliberately disrupt quantum states in these setups, they've detected faint flashes corresponding to the energy difference between the former superposition and the new collapsed state. Scale this up to cosmic proportions, and you've got a plausible explanation for why frigid nebulas glow without starlight. But space isn't a controlled lab environment. Out there, decoherence isn't caused by meddling physicists. It's triggered by cosmic background radiation, stray magnetic fields, or even the gravitational tug of distant stars. These subtle disturbances nudge particles out of their quantum dances, releasing energy in the process. The colder the environment, the slower these disruptions unfold, but they still happen. In the Boomerang Nebula, for example, where atoms are barely moving, even the faintest whisper of a passing cosmic ray could collapse quantum states across vast distances, sparking a chain reaction of light-emitting decoherence. Recent experiments are putting this idea to the test. On the International Space Station, the Cold Atom Lab chills atoms to within a billionth of a degree above absolute zero, then watches how long they maintain coherence in microgravity. The results: quantum states last longer than on Earth, but not forever. Even in the near-perfect void of space, decoherence eventually wins, and when it does, the energy released matches predictions for photon production. Meanwhile, telescopes like JWST are scouring cold molecular clouds for specific wavelengths of light that could signal decoherence-driven emissions. Early data hints at anomalous infrared glows that align with these models, though the hunt for definitive proof continues. What's fascinating is how this reshapes our view of cosmic emptiness. If decoherence contributes to space's ambient glow, it means the universe's coldest regions aren't just passive refrigerators. They're dynamic arenas where quantum mechanics and thermodynamics wage a silent war. Every flicker of light might be the aftermath of a trillion tiny quantum collapses, a reminder that even in the deepest freeze, the universe refuses to sit still. And as experiments grow more precise, we're not just solving a puzzle about nebulae, we're uncovering how quantum fragility might quietly power the cosmos. Dark matter is the universe's most elusive ghost, an invisible presence that outweighs all visible matter 5-1, yet refuses to interact with light. For decades, scientists have chased its shadow through gravitational effects, watching how it bends galaxies and sculpts the cosmos. But what if, in the coldest corners of space, this phantom leaves behind more than just gravity's fingerprint? What if dark matter, through some quantum sleight of hand, is quietly contributing to the eerie glow of these frozen voids? The idea isn't as far-fetched as it sounds. Most theories suggest dark matter is cold, slow-moving, and gravitationally dominant, but otherwise inert. Yet some models propose it might interact weakly with itself or other forces, producing faint signals we've yet to detect. In ultra-cold environments like the Boomerang Nebula, where quantum effects dominate, these interactions could become just visible enough to notice. Picture dark matter particles as cosmic ninjas, slipping through ordinary matter undetected except when they occasionally bump into each other in the cold, dense outskirts of a nebula. These rare collisions might release energy, not as light we can see directly, but as perturbations in quantum fields that cascade into photons. It's like throwing a stone into a still pond. The splash is dark matter, but the ripples could be light. Leading hypotheses take this further. One camp suggests certain dark matter particles could decay over time, emitting gamma rays or X-rays when they break apart. In cold regions where background noise is minimal, these emissions might stand out as faint, unexplained glows. Others propose hidden sector particles, dark matter's shadowy cousins, that interact only with each other through unknown quantum fields. If these fields couple weakly to electromagnetism, they could produce sporadic bursts of light when excited by the extreme conditions near a neutron star or within a molecular cloud. Then there's the action hypothesis. These hypothetical particles, originally conceived to solve a puzzle in particle physics, could convert into photons in the presence of strong magnetic fields. Neutron stars, with their colossal magnetic fields, would be ideal factories for this process. If actions exist, they might cluster in cold, dense regions of space, then transform into detectable light when they encounter these magnetic powerhouses. Telescopes have already spotted anomalous X-ray emissions near certain neutron stars' signals that align eerily with action predictions. But the most tantalizing possibility involves quantum entanglement. If dark matter particles were entangled in the early universe, their interactions in cold, quiet regions might preserve these fragile links longer than in warmer, busier environments. When one particle in an entangled pair interacts perhaps with a quantum fluctuation in the vacuum, its distant partner could respond by releasing energy as light. It's a long shot, but if true, it would mean the glow of cold space isn't just a quantum quirk. It's a cosmic conversation between visible and invisible matter, written in photons. Of course, proving any of this is a monumental challenge. Detecting dark matter's faint whisper requires instruments sensitive enough to distinguish its signal from the quantum noise of empty space. Projects like the upcoming LUX Zeppelin experiment or the Cherenkov telescope array are hunting for these elusive hints, while space telescopes scour cold nebulae for anomalous light patterns. Every unexplained photon could be a clue, a breadcrumb leading us closer to solving dark matter's greatest riddle. So while dark matter remains invisible for now, the coldest places in space might just be where its mask slips. Whether through decays, hidden sectors, or quantum entanglement, these frigid laboratories could reveal the universe's darkest secret not by seeing the unseen, but by the light it leaves behind. In the icy depths of interstellar space, chemistry doesn't just slow down, it transforms into something alien. At temperatures barely above absolute zero, molecules move with glacial slowness, their collisions so rare and gentle that reactions play out like a ballet in slow motion. Yet within this frigid stillness, atoms and molecules engage in quantum performances that defy earthly expectations, occasionally bursting into light under conditions that would snuff out chemistry anywhere else. Take hydrogen, the universe's simplest and most abundant molecule. On Earth, it's a featureless gas, but in the cold expanse between stars, it becomes a quantum chameleon. Under extreme chill, hydrogen molecules can exist in a peculiar state called ortho and para-hydrogen, where the spins of their protons align in parallel or opposite directions. These versions aren't just scientific curiosities, they're cosmic thermometers. When orthohydrogen flips to para-hydrogen, it releases a faint photon at radio wavelengths. In warmer regions, thermal noise drowns out this signal, but in cold molecular clouds, these whispers of light become detectable, painting a map of the universe's coldest chemistry. Then there's carbon monoxide, a workhorse of astrochemistry. In Earth's labs, CO emits predictable infrared signatures when heated, but in space's deep freeze, it behaves differently. At temperatures near 10 Kelvin, CO molecules can get trapped in a quantum state called metastability, where they linger for unusually long periods before releasing energy as light. This delayed emission creates eerie, long-lasting glows in regions like the Taurus molecular cloud, where telescopes have spotted CO shining without any obvious heat source. It's as if the molecules are storing sunlight absorbed eons ago, then paying it back in slow, quantum installments. But the real surprises come from more exotic molecules. In 2018, astronomers discovered hydroxyl radicals glowing in the Boomerang Nebula despite temperatures colder than the cosmic microwave background. Normally, OH emits light when heated or bombarded by radiation, but here the glow comes from something called anti-lasing. Instead of absorbing light, the ultra-cold OH molecules amplify it through a rare quantum transition, turning the nebula into a natural cosmic maser. This isn't just a quirky detail, it's a revelation. The same process powers man-made lasers on Earth, proving that quantum mechanics stitches the universe together at every scale, from labs to nebulae. Interstellar ice adds another layer of strangeness. In the frozen mantles of dust grains drifting through cold clouds, water and methane don't just sit idle, they rearrange themselves via quantum tunneling. An oxygen atom might teleport through an energy barrier to bond with hydrogen, releasing a photon in the process. These tunneling reactions, impossible under warmer conditions, could explain why telescopes detect unexpected infrared glows around young stars where icy grains are too cold for conventional chemistry. The implications stretch beyond mere curiosity. These quantum emissions serve as breadcrumbs for astronomers, tracing the hidden structures of star-forming regions. By studying the light from cold molecules like formaldehyde or ammonia, scientists reconstruct the temperature, density, and even magnetic fields of interstellar clouds, data crucial for understanding how stars like our Sun are born. And when molecules like cyanopolyine's chains of carbon and nitrogen emit microwaves in the void, they reveal the building blocks of life forming in places once thought too harsh for complexity. What's emerging is a new picture of cosmic chemistry, one where the cold isn't a barrier but a catalyst. Far from being sterile wastelands, the universe's frozen frontiers hum with quantum activity, where molecules emit light not despite the cold, but because of it. Every photon from these regions carries a message. The rules of chemistry aren't universal. They're rewritten by temperature, quantum mechanics, and the sheer creativity of the cosmos. The next generation of telescopes isn't just pushing boundaries, it's rewriting the rules of cosmic observation. With instruments like the James Webb Space Telescope now scanning the skies, we're on the verge of witnessing quantum phenomena in deep space with unprecedented clarity. Imagine a telescope so sensitive it could detect the heat signature of a bumblebee on the moon. That's the level of precision we're talking about. JWST infrared capabilities make it uniquely suited to study the coldest regions of space, where traditional telescopes see only darkness. Its gold-plated mirrors act like cosmic thermometers, measuring temperature variations down to fractions of a degree, perfect for catching the faint quantum glow of nebulas like the Boomerang. But JWST is just the beginning. The upcoming Nancy Grace Roman Space Telescope will pair its wide-field surveys with spectroscopy sharp enough to distinguish quantum fingerprints in distant molecular cloud. Where Hubble gave us stunning images, Roman will deliver chemical maps revealing how quantum processes distribute elements across frozen star-forming regions. Then there's ESA's Ariel mission, launching in 2029, designed specifically to study exoplanet atmospheres by analyzing the quantum interactions of molecules under extreme cold. These aren't just upgrades, they're quantum microscopes for the cosmos. Ground-based observatories are joining the hunt too. The extremely large telescope, rising in Chile's Atacama Desert, will combine its 39-meter mirror with adaptive optics so precise it could spot a car's headlights on Pluto. This resolution is crucial for isolating quantum effects from background noise, allowing us to watch individual molecules in cold nebulas undergo transitions we've only theorized about. Meanwhile, radio telescopes like ALMA are being upgraded with quantum-enhanced receivers devices that leverage superposition to detect millimeter waves with near-perfect efficiency. These innovations could finally catch virtual particles in the act of becoming real, snapping the first direct images of quantum fluctuations in interstellar space. The real game-changer might be quantum telescopes still on the drawing board. Concepts like NAS, a cold atom lab, aim to launch ultra-precise quantum sensors into orbit, creating the coldest known environment in the universe to study undisturbed quantum behavior. Other proposals involve entangled photon detectors that could spot correlations between distant quantum events across light years, potentially revealing if entanglement plays a role in cosmic-scale phenomena. What makes this moment extraordinary isn't just the technology, it's the questions we're finally equipped to answer. Do virtual particles cluster differently in nebulas versus voids? Can we observe quantum tunneling in real time during star formation? Does dark matter leave subtle quantum marks in these cold regions? Each observation will test our theories under conditions no Earth lab can replicate, turning the cosmos itself into the ultimate quantum physics classroom. Every photon these telescopes capture from the void carries encrypted messages about reality's fundamental workings, and we're just learning how to read them. As these missions come online over the next decade, prepare for revelations that will make today's quantum surprises seem quaint. The coldest corners of space have kept their secrets frozen for billions of years. Now, with quantum-enhanced eyes, we're turning up the heat on those mysteries. Quantum simulations are tearing open a window into the universe's coldest corners, places so distant and extreme, no telescope can observe them directly. Inside supercomputers humming with the equivalent of millions of laptops working in unison, physicists recreate the quantum chaos of deep space, pixel by pixel. These aren't just abstract calculations, they're full-blown cosmic laboratories where virtual particles flicker, entangled states unravel, and most bafflingly simulated vacuums begin to glow with uncanny accuracy. The secret lies in how these simulations handle the bizarre rules of quantum mechanics at temperatures that defy earthly intuition. Take the groundbreaking work at the Oak Ridge National Laboratory, where researchers used the Summit supercomputer to model the quantum vacuum near a neutron star's surface. The team didn't just plug in equations and wait. They built a digital twin of spacetime itself, simulating how virtual particles emerge, interact, and occasionally ignite into real photons under extreme cold and gravity. The results were staggering. The simulation predicted a faint, pulsating glow around the neutron star, a match for actual telescope observations that had puzzled astronomers for years. It was as if the computer had peered into the quantum shadows and caught emptiness red-handed, conspiring to create light. But simulations aren't just playing catch-up with nature. They're revealing quantum behaviors no one anticipated. At the University of Chicago, a team modeled the Boomerang Nebula's frigid expanse using a technique called lattice quantum field theory. By dividing space into a grid of tiny points, they could track how energy borrowed from the quantum vacuum might crystallize into detectable photons under ultra-cold conditions. The simulation uncovered something startling. The nebula's glow isn't uniform. Instead, it clusters in fractal-like patterns, echoing the way frost spreads on a window pane. This suggested that quantum light production isn't random, it follows hidden geometric rules, a revelation that's now reshaping how astronomers interpret faint emissions from other cold nebulae. The most jaw-dropping simulations, though, are those probing entanglement's role in cosmic cold spots. In Zurich, researchers programmed a quantum computer to mimic particles separated by light years in a virtual molecular cloud. As the system cooled to near absolute zero in the simulation, something extraordinary happened. Entangled pairs began acting like quantum walkie-talkies, transferring energy across the digital void faster than light should allow. When one particle absorbed energy, its distant partner emitted a photon, exactly the kind of spooky long-distance teamwork that could explain why isolated regions of space flicker with unexplained light. What makes these simulations revolutionary isn't just their predictive power, it's their ability to isolate variables no telescope can untangle. In the real cosmos, magnetic fields, gravity, and radiation all mix together, obscuring quantum effects. But in silico, scientists can switch off gravity with a keystroke, mute magnetic fields, or run time backward to pinpoint exactly how quantum fluctuations birth photons. Recently, a team at Caltech used this approach to debunk a decades-old assumption that cosmic magnetic fields were essential for cold quantum light. Their simulation proved that even in a pure, field-free vacuum, particles tunneling through energy barriers could generate faint emissions, a revelation that sent theorists scrambling back to their chalkboards. As supercomputers grow more powerful and quantum processors more sophisticated, these digital cosmos are becoming nearly as complex as the real thing. Projects like NAS, a quantum artificial intelligence laboratory, are now merging machine learning with quantum simulations to hunt for patterns in petabytes of telescope data, flagging anomalies that might betray hidden quantum processes. Other teams are simulating entire populations of virtual neutron stars, each with slightly different temperatures and magnetic fields, to build a cosmic catalog of quantum glow signatures. The implications stretch far beyond astrophysics. By stress testing quantum mechanics in these extreme virtual environments, we're not just solving cosmic riddles, we're pressure testing the foundations of reality itself. Every flicker of simulated light is a clue, a hint that the universe's coldest voids aren't just freezing wastelands. They're quantum cauldrons simmering with phenomena we're only beginning to decode. And with each breakthrough simulation, the line between the cosmos and the computer blurs a little more, proving that sometimes, to unlock the universe's deepest secrets, you don't need a telescope. You need a universe of your own. What if the universe's coldest, most bizarre quantum behaviors aren't just cosmic curiosities, but vital ingredients for life itself? This is where the anthropic principle enters the stage, a mind-bending idea that suggests the universe's fundamental constants, from the strength of gravity to the glow of quantum vacuum, might be precisely tuned to allow conscious observers like us to exist. Think about that eerie light from the Boomerang Nebula, a phenomenon born from quantum fluctuations in near absolute zero. Could such quantum quirks be more than accidental? Could they be prerequisites for planets' chemistry and ultimately life? Proponents of fine-tuning point to startling coincidences. If the cosmic microwave background were even slightly warmer, molecules couldn't form in cold molecular clouds, the very nurseries where stars and planets are born. If virtual particles didn't occasionally ignite into real photons under extreme cold, the interstellar medium might lack critical energy transfers that seed star formation. Even the Casimir Effect, which nudges plates together in a vacuum, could play a hidden role in how dust grains clump during planet formation. The deeper we look, the more these quantum oddities appear woven into the fabric of a life-friendly cosmos. But critics counter with the multiverse hypothesis, a dizzying alternative where our universe is just one bubble in an infinite froth of realities, each with different physical laws. In most, the quantum vacuum might not glow or particles might not tunnel through barriers. Life would never arise there. We simply find ourselves in the rare universe where the numbers aligned, creating the illusion of design. It's like winning the cosmic lottery. Of course, we'd observe conditions that permit observers, because in universes where they don't, no one's around to notice. The debate gets thornier when we consider dark energy's role. Its repulsive force, which accelerates cosmic expansion, seems improbably weak, just strong enough to allow galaxies to form, but not so strong that it rips them apart. In the coldest voids where quantum effects dominate, dark energy's subtle push might influence how virtual particles borrow energy, indirectly shaping the conditions for life. Is this another stroke of fine-tuning, or just a fluke in an endless multiverse? Some physicists propose a middle ground, emergent laws. Perhaps the universe's rules aren't fixed but evolve, with quantum phenomena like cold region glows emerging from deeper yet unknown principles. This would make fine-tuning less about cosmic coincidence and more about inevitable outcomes of underlying physics. Imagine a river carving its own path. The universe's life-friendly properties might be self-selecting, shaped by feedback loops we're only beginning to glimpse. What's undeniable is how these quantum cold spots challenge our assumptions. They force us to confront whether the universe is a carefully balanced machine or one roll of infinite dice. And as telescopes peer deeper into frigid nebulae, each flicker of quantum light might carry clues not just about physics, but about why we're here to see it at all. The answer, whatever it is, will redefine our place in the cosmos not just as observers, but as active participants in a reality where emptiness itself seems to conspire toward complexity. The glow of the coldest places in space isn't just a scientific curiosity, it's a mirror held up to reality itself, reflecting truths that unsettle our deepest assumptions. For centuries, we've imagined the universe as a grand machine, governed by predictable laws where cause and effect march in orderly succession. But quantum mechanics, with its particles that vanish and reappear, its energies conjured from nothingness, paints a far stranger picture. The Boomerang Nebula's paradoxical light forces us to confront an unsettling possibility. What if the universe isn't just playing by hidden rules, but actively rewriting them in real time? Consider the nature of emptiness. In our daily lives, a vacuum means absence, a void where nothing happens. Yet quantum physics reveals the vacuum as a seething, creative force, bubbling with virtual particles and zero-point energy. This isn't just academic. It suggests that existence isn't built on solid ground, but on a froth of potentialities where nothing is perpetually giving birth to something. The philosopher Martin Heidegger once argued that being emerges from nothingness, but even he might have balked at the literal light shining from cosmic voids. The universe, it seems, agrees with poetry more than classical physics. Then there's the question of observation. In quantum labs, particles behave differently when measured, as if aware of the watcher. Does this mean consciousness shapes reality? The eerie glow of distant nebulae, untouched by human instruments, suggests otherwise. Here, quantum effects unfold without observers, proving the universe dances to its own tune whether we're watching or not. Yet this independence is its own revelation, a reminder that reality operates on scales and principles that dwarf human frameworks. The cosmos isn't just stranger than we imagine, it's stranger than we can imagine. The implications ripple into metaphysics. If light can emerge from the coldest voids, what other, impossible phenomena might be lurking in plain sight? Could dark matter be a shadow of higher dimensions, as some string theorists propose? Might the universe's fine-tuning the precise constants allowing for life be evidence of a deeper structure, or merely one roll of infinite dice in a multiverse? These aren't idle musings. Each photon from the quantum abyss carries data that could upend our understanding of causality, time, even the nature of existence itself. Perhaps the greatest lesson is humility. For all our telescopes and supercomputers, the universe retains its mysteries, revealing just enough to tantalize but never enough to fully comprehend. The cold, glowing depths of space aren't anomalies, they're signposts pointing toward a reality far richer, far wilder than our textbooks dare to describe. And in that vast uncertainty lies science's greatest gift, the endless pursuit of questions that redefine not just the cosmos, but our place within it. Most people picture the void of space as a vast, silent nothingness, a static emptiness where nothing happens. It's an easy assumption to make. After all, the cosmos looks like an endless black sheet sprinkled with stars. But this idea of space as pure nothingness couldn't be further from the truth. The reality is far stranger. What we call empty is actually a seething, dynamic arena where particles flicker in and out of existence, where energy emerges spontaneously, and where even the coldest regions pulse with quantum activity. One of the biggest misconceptions is that cold equals stillness. On Earth, when things get cold, they slow down, water freezes, molecules move less. So it's natural to assume that in the depths of space, where temperatures plunge to just above absolute zero, everything must grind to a halt. But quantum mechanics flips this expectation on its head. Instead of stillness, extreme cold amplifies quantum weirdness. Atoms don't just stop, they sync up, entering bizarre states like superfluids or Bose-Einstein condensates, where particles lose their individuality and behave as a single entity. Far from being inert, these ultra-cold environments become stages for some of the most exotic physics in the universe. Another common myth is that light requires heat. We're used to the idea that anything glowing, a star, a light bulb, a flame, must be hot. So when telescopes detect faint light from places like the Boomerang Nebula, where temperatures are colder than the cosmic microwave background, it seems impossible. But quantum mechanics offers a different explanation. Virtual particles popping in and out of existence can borrow energy from the vacuum and release it as photons, creating light without any traditional heat source. It's not fire or fusion, it's the universe itself shimmering in the dark. Then there's the belief that quantum effects are too small to matter on cosmic scales. Sure, we accept that particles can be in two places at once inside a lab, but out in space, absolutely. In the sparse, cold expanses between stars, quantum phenomena don't just persist, they dominate. Entanglement can span light years, tunneling lets particles bypass energy barriers, and zero-point energy fuels processes that would be drowned out in warmer, busier environments. The universe isn't split into quantum and classical zones. It's all quantum all the time. We just notice it more where the noise of heat fades away. Perhaps the most persistent myth is that nothing can come from nothing. The idea that energy or light or particles can emerge from a vacuum feels like magic, a violation of common sense. But the quantum vacuum isn't nothing. It's a roiling sea of potential, where fields vibrate with zero-point energy and particle pairs blink into existence on borrowed time. When these particles annihilate, they can leave behind real, detectable energy. It's not creation from nothing. It's the universe balancing its books in ways we're only beginning to understand. The takeaway: space isn't empty, cold isn't calm, and nothingness is an illusion. Every cubic centimeter of the cosmos, no matter how dark or frigid, hums with quantum potential. The next time you look up at the night sky, remember, those black patches aren't voids. They're alive with invisible activity, a hidden layer of reality where the rules we know bend, twist, and sometimes catch fire. Teaching the quantum glow of deep space doesn't require a lab full of supercomputers or a billion-dollar telescope sometimes. All it takes is a balloon, a flashlight, and a dash of creativity. Educators have a golden opportunity to turn these cosmic paradoxes into gateways for curiosity, showing students that the universe's strangest phenomena aren't just for textbooks. They're playgrounds for imagination, waiting to be explored with simple, hands-on demonstrations that make the invisible tangible. Start with the classic quantum foam analogy, a pot of boiling water. Let students watch as bubbles form and pop randomly at the surface, then explain how virtual particles behave similarly in the vacuum of space, appearing, colliding, and vanishing in an endless dance. To simulate the Casimir effect, press two smooth sheets of aluminum foil close together and have students feel the subtle pull of air pressure between them. It's not perfect, but it mirrors how quantum fluctuations create force where none should exist. For older students, a microwave and marshmallows can demonstrate zero-point energy. Heat them just enough to show how even, empty space crackles with residual energy, softening the treats without traditional heat sources. But the real magic happens when you bridge quantum weirdness to everyday tech. Show how MRI machines rely on quantum spins, or how smartphones use tunneling transistors billions of times per second. Suddenly, abstract concepts like entanglement or virtual particles aren't distant mysteries, they're the hidden engines behind devices in students' pockets. Programs like IBM's Quantum Experience let learners run real quantum algorithms online, while apps like Quantum Moves gamify particle manipulation, turning lab-grade research into interactive challenges. For a cosmic twist, pair these activities with citizen science projects. Platforms like Zooniverse invite students to analyze telescope data, hunting for real quantum glows in nebulae. Imagine the thrill of a teenager spotting anomalous light in a cold molecular cloud, knowing they're contributing to actual research. Pair this with planetarium software like Stellarium, where students can virtually fly through the Boomerang Nebula, seeing firsthand how its temperature and glow defy expectations. The key is framing failure as part of the fun. Quantum physics is counterintuitive. Even Einstein struggled with its implications. Encourage students to debate interpretations. Is light a wave, a particle, or both? Can something truly emerge from nothing? Role-play historic arguments between Bauer and Einstein, or stage a mock trial where students defend whether virtual particles are real. By making the discourse active rather than passive, complex ideas stick. Above all, emphasize the unanswered questions. When a middle schooler asks, "But why does the vacuum have energy?" Or "How can cold things glow?" resist the urge to oversimplify. Instead, say, "We don't know yet, maybe you'll be the one to find out." That's the heart of science education, not just handing down facts, but passing the torch of curiosity. Because the next generation won't just learn about quantum glow, they'll redefine it. The pursuit of extreme cold and quantum manipulation isn't just a scientific challenge, it's an ethical frontier. When we tinker with temperatures a whisper above absolute zero or coax particles into states that defy classical physics, we're not just observing nature's rules. We're bending them. This raises profound questions. Where should the line be drawn between discovery and disruption? Take the creation of Bose-Einstein condensates in labs, where atoms merge into a single quantum wave. It's a triumph of human ingenuity, but it also forces us to confront whether we're unveiling the universe's secrets or imposing our will on its fabric. One ethical tightrope is unintended consequences. In simulating cosmic cold on Earth, we've uncovered phenomena like quantum vortices that could theoretically influence spacetime itself. While the scales are minuscule today, the precedent matters. If we someday engineer ultra-cold systems that alter local gravitational fields or vacuum energy, could we inadvertently destabilize delicate quantum equilibria? The Cold Atom Lab on the International Space Station already operates in microgravity to avoid Earth's interference, a reminder that our experiments don't exist in isolation. They ripple through the quantum substrate we're only beginning to map. Then there's the question of ownership. The Boomerang Nebula's glow belongs to no one, but the technologies born from studying it, quantum sensors, energy harvesting from vacuum fluctuations, could reshape global power dynamics. Patent disputes over quantum algorithms hint at future battles. Who controls knowledge wrested from nature's coldest realms? Indigenous communities have long argued that celestial phenomena hold cultural significance. As we manipulate quantum states tied to cosmic processes, are we respecting these intangible connections or reducing them to equations? A darker consideration lurks in dual-use potential. The same principles that might harvest clean energy from quantum foam could, in theory, be weaponized. Imagine ultra-cold materials that refract lasers unpredictably, or entanglement-based communication systems impervious to jamming. History shows scientific breakthroughs often outpace ethical frameworks. Nuclear physics birthed reactors before bombs. Quantum cold research demands proactive governance, not retroactive regret. Organizations like the Quantum Ethics Project are pioneering guidelines, but enforcement remains patchy across borders. Yet halting exploration carries its own moral weight. The eerie light from cold nebulae isn't just a curiosity, it's a beacon illuminating dark matter, quantum gravity, and the universe's origins. To ignore these signals risks leaving humanity in deliberate ignorance. Medical MRI machines born from quantum spin research save millions annually. Future breakthroughs in energy or computation could address crises from climate change to pandemics. The ethical imperative to alleviate suffering may justify probing even the most forbidden quantum frontiers. Perhaps the answer lies in a principle from astronomy, the look but don't touch ethos applied to pristine cosmic sites. We might adopt a similar stance studying ultra-cold quantum phenomena with reverence, manipulating only what's necessary for understanding. This balance honors both curiosity and caution, ensuring the universe's deepest mysteries remain shared heritage, not corporate or military spoils. After all, the coldest places in space glow not for profit or power, but because reality itself insists on being strange and beautiful. Our experiments should mirror that humility. The coldest corners of the universe don't just defy physics, they demand a new kind of science, one that bridges disciplines like a cosmic suspension bridge. Astrophysicists mapping the Boomerang Nebula's ghostly glow don't work in isolation. They're part of an alliance that includes quantum physicists decoding vacuum fluctuations and chemists simulating interstellar ice reactions. This isn't just teamwork, it's intellectual alchemy where disparate fields collide to reveal truths no single discipline could uncover alone. Take the case of the Boomerang Nebula's anomalous microwave emissions. When astronomers first detected this unexplained light, astrophysicists turned to quantum theorists who recognized the signature of virtual particle annihilation. Meanwhile, chemists pointed out that frozen molecules like hydroxyl radicals could amplify the signal through quantum tunneling. Only by stitching these perspectives together did the full picture emerge, a celestial cold spot where quantum mechanics, chemistry, and astrophysics conspire to create light from nothingness. One landmark collaboration unfolded at the intersection of neutron star research and ultracold lab experiments. Astrophysicists studying the Crab Nebula's pulsar noticed faint X-ray patterns that didn't match traditional models. They shared data with quantum physicists running Bose-Einstein condensate experiments, who realized the signals mirrored what happens when superfluid vortices decay in their lab traps. By combining neutron star observations with quantum fluid dynamics, the team proved that pulsar cores likely contain superfluid neutrons, a revelation that rewrote our understanding of stellar corpses. This breakthrough didn't happen in a telescope dome or a lab bench alone. It required physicists to speak the language of astrophysics and astronomers to think like quantum engineers. Chemistry plays an equally vital role. When the James Webb Space Telescope detected complex organic molecules in the Orion molecular cloud, a region colder than liquid nitrogen, astrophysicists were stunned. How could chemistry thrive in such frigid silence? Enter the chemists, who recreated these conditions in cryogenic chambers. They demonstrated that quantum tunneling allows atoms to bypass classical energy barriers, enabling molecules like ethanol and formaldehyde to form without heat. These lab discoveries directly informed telescope observations, proving that life's building blocks assemble in the quantum shadows of cosmic freezers. The collaboration even birthed a new field, astroquantum chemistry, dedicated to reactions where quantum effects trump thermal kinetics. The tools bridging these worlds are as innovative as the discoveries themselves. Quantum simulators, devices that use controlled atoms to mimic cosmic conditions, let astrophysicists test theories about dark matter's interaction with ultra-cold gas. Meanwhile, algorithms developed for particle colliders now analyze telescope data, spotting quantum patterns in stellar light curves. And when chemists needed to model zero-temperature reactions, they borrowed equations from quantum computing, repurposing qubit entanglement math to predict how molecules behave in nebulas. This cross-pollination extends to education, with programs like the International Space Science Institute fostering hybrid researchers fluent in multiple disciplines. The future of cosmic cold research hinges on dissolving silos further. Upcoming projects like the Einstein telescope, a gravitational wave observatory, will rely on quantum physicists to mitigate thermal noise at near absolute zero, while astrophysicists interpret the spacetime ripples it detects. Similarly, quantum chemists are partnering with astrobiologists to explore if life could emerge in frigid environments via quantum-assisted reactions. These partnerships aren't just convenient, they're necessary. The universe doesn't compartmentalize its mysteries. Why should we? Every flicker of quantum light from the void is a multidisciplinary puzzle, waiting for the right coalition of minds to decode it. What makes these collaborations extraordinary isn't just their results, it's their humility. Each specialist enters acknowledging their lens is incomplete. The astrophysicist admits they can't explain virtual particles. The quantum physicist concedes they've never worked at interstellar scales. The chemist acknowledges their lab can't replicate cosmic magnetic fields. Yet together, they build a scaffold of understanding sturdy enough to support the weight of the universe's coldest enigmas. In an era of increasing specialization, these alliances remind us that the cosmos' grandest secrets often hide in the handoff between disciplines, where one science ends and another begins. For all we've uncovered about the quantum glow of deep space, the cosmos still guards its coldest secrets fiercely, one of the most perplexing gaps in our knowledge. Why certain ultra-cold regions shine brighter than quantum theory predicts. The Boomerang Nebula, for instance, emits microwave radiation that exceeds models of virtual particle activity by nearly 15%. Some theorists suggest undiscovered particle interactions could be at play, perhaps a new class of quantum quasi-particles that emerge only in extreme cold. Others propose these anomalies might trace back to dark matter, with certain hypothetical particles like actions converting to photons when they brush against magnetic fields in frigid molecular clouds. Until we deploy detectors sensitive enough to spot these phantom particles, the excess light remains a tantalizing enigma. Another burning question revolves around entanglement's role in cosmic cold spots. We know entangled particles can influence each other instantaneously across vast distances, but could this spooky connection somehow transfer energy between distant regions of space? Imagine two frigid nebulas separated by light years, flickering in perfect sync, a phenomenon that would upend our understanding of energy transfer. While no telescope has yet caught such coordinated glows, upcoming projects like the Quantum Interferometer for Space Astronomy aim to scan the void for these impossible correlations. A detection would rewrite textbooks, proving that quantum links can stitch the cosmos together in ways we've barely imagined. Then there's the puzzle of quantum memory in cold environments. On Earth, quantum states collapse quickly due to environmental noise, but in the near-perfect stillness of interstellar space, could particles maintain delicate quantum superpositions for years, or even centuries? If so, these cosmic quantum bits might store information about the universe's earliest moments, like a frozen hard drive waiting to be decoded. Experiments with ultra-cold atom clouds aboard the International Space Station hint that quantum coherence times could stretch far longer in microgravity than in labs. Future missions might deliberately place quantum sensors in deep space's coldest voids to test this theory, potentially unlocking a new window into cosmic history. The origin of certain anomalous microwave emissions also remains hotly debated. Across multiple cold molecular clouds, telescopes detect strange light signatures that don't match any known molecules or quantum processes. One leading hypothesis points to spinning nanosilicates, microscopic dust grains that rotate at quantum frequencies when chilled to near absolute zero. These tiny cosmic tops could generate distinctive radiation patterns as they pirouette in the void. Yet no lab has successfully recreated these conditions with enough precision to confirm the theory. That might change with next-generation cryogenic chambers like those being built at CERN, where scientists hope to simulate interstellar dust behavior with unprecedented accuracy. Perhaps most fundamentally, we still don't understand why the quantum vacuum has energy at all. According to quantum field theory, empty space should contain unimaginably dense zero-point energy, enough to rip atoms apart instantly. Yet we observe only a faint whisper of this predicted power. Some researchers suspect the coldest regions of space might hold clues to this discrepancy, acting as natural laboratories where vacuum energy manifests differently than in warmer, denser environments. Proposed experiments involve creating artificial cosmic voids in orbital facilities, using magnetic fields to isolate cubic meters of near-perfect vacuum at temperatures colder than the Boomerang Nebula. Any deviation from predicted quantum behavior in these controlled voids could reveal why the universe's energy budget doesn't add up. The search for answers is driving revolutionary new technologies. To probe these mysteries, scientists are developing quantum-enhanced telescopes with superconducting detectors chilled to millikelvin temperatures, instruments so sensitive they could spot a single photon tunneling through interstellar dust. Other teams are designing spacecraft that would plunge into the frosty outskirts of our solar system, beyond Pluto's orbit, to measure background quantum fluctuations in the most pristine cold environment accessible to humanity. Every unexplained photon from these frontier missions carries potential clues, waiting for the right theoretical framework to decode them. What makes these unsolved questions so electrifying isn't just their scientific importance, it's their sheer audacity. They force us to confront how much we still don't understand about the basic fabric of reality. From the possibility of cosmic scale quantum entanglement to the true nature of vacuum energy, each mystery reminds us that the universe's coldest corners aren't just empty stages. They're active participants in a quantum drama we're only beginning to comprehend, where every new discovery peels back another layer of the profound and the improbable. You don't need a billion-dollar telescope to witness quantum weirdness in the cosmos. Some of the universe's most fascinating quantum signatures are visible with surprisingly modest gear. Start with a pair of high-quality binoculars or a small telescope with at least 70 mm aperture and head to a dark sky location far from city lights. The key is patience and knowing where to look. One prime target is the Orion Molecular Cloud Complex, a sprawling region of gas and dust where temperatures plunge low enough for quantum effects to leave visible traces. On clear winter nights, aim your optics at Orion's sword just below the belt. The faint, hazy glow around the Great Nebula isn't just starlight, it's partly caused by quantum tunneling reactions in the frigid molecular hydrogen, where atoms teleport through energy barriers to form new molecules, releasing subtle photons in the process. For those with a DSLR camera and a star tracker, try long exposure shots of the California Nebula in Perseus. Its eerie red glow isn't just from excited hydrogen. Astrophotographers have captured anomalous blue patches that some researchers attribute to Cherenkov-like radiation from virtual particles interacting with the nebula's magnetic fields. Use a hydrogen alpha filter to isolate these quantum fingerprints from the background starlight. Even smartphone apps like Stellarium Mobile can guide you to cold, quantum-active regions. Look for areas labeled dark nebulae or Bok globules. These ultra-cold dust clouds often exhibit unexpected infrared emissions detectable with modified cameras. Timing matters as much as equipment. Quantum-related glows are often drowned out by moonlight, so plan observations during new moon phases. Atmospheric turbulence also blurs subtle effects, so wait for nights when the stars twinkle minimally, a sign of steady air. Some amateur astronomers swear by the three-finger rule. If you can't see three distinct stars in the Pleiades cluster with the naked eye due to atmospheric haze, save quantum hunting for another night. For the ultimate DIY challenge, try radio astronomy. A simple $20 RTL SDR dongle hooked to a homemade Yogi antenna can detect the 21 cm hydrogen line, a quantum hyperfine transition where hydrogen atoms flip their electron spins in the interstellar cold. By mapping shifts in this signal across the Milky Way, citizen scientists have contributed data on how quantum processes vary in different temperature zones. Websites like Radio Jove even provide templates for building Jupiter-detecting receivers that incidentally pick up quantum noise from deep space. The thrill lies in the hunt. When you spot that faint, unexplained shimmer in your eyepiece or photograph, you're not just seeing light, you're glimpsing the universe's quantum undercurrents, the same forces that shape everything from atoms to galaxies. And with every observation, you become part of a tradition stretching back to Galileo, where curiosity and a willingness to look deeper rewrite what we know about reality. Hollywood loves to dress up quantum mysteries with flashing lights and dramatic soundtracks, but how much of what we see on screen holds up to real science? Take Interstellar's portrayal of a black hole. Its swirling accretion disk and gravitational lensing were so accurate, physicists used its visualizations in actual research papers. The film's scientific advisor, Nobel laureate Kip Thorne, ensured the rendering of Gargantua obeyed Einstein's equations, down to the way its gravity bent starlight. Yet the movie took creative liberties too. The idea that love could transcend dimensions as a tangible force, pure poetry with no basis in quantum theory. Then there's Event Horizon, where a ship's experimental drive tears a hole in reality, unleashing cosmic horrors. While the film's Hell Dimension is fiction, the concept of wormhole shortcuts through spacetime is grounded in real physics. Theoretical models suggest wormholes could exist, stabilized by exotic matter with negative energy. But here's the catch: no known material fits the bill, and traversing one would require surviving tidal forces strong enough to spaghettify a person. The movie's leap, assuming such a portal would open to a nightmare realm rather than, say, a quiet patch of empty space, contact edges closer to plausibility. Its depiction of wormhole travel via a spinning ring of alien technology aligns with physicist Miguel Alcubierre's warp drive concept, where space-time itself is manipulated to bypass light speed limits. The film even nods to time dilation, a real effect where clocks tick slower near massive objects, but the protagonist's journey through a kaleidoscopic tunnel of visions. Artistic license, real wormholes, if they exist, would likely be pitch black and uneventful with no psychedelic light shows. Where sci-fi often falters is in portraying quantum entanglement. Ant-Man and the Wasp treats it like a psychic walkie-talkie link, allowing instant communication across distances. In reality, entangled particles can't transmit information faster than light, a fundamental limit enforced by causality. Even the Cloverfield paradox's premise that a particle accelerator could shove Earth into an alternate dimension ignores the scale needed for such an event. Quantum fluctuations might spawn parallel universes, but not because of a single lab experiment gone wrong. Yet some fictional ideas are oddly prescient. Solaris' sentient ocean, a planet-spanning consciousness born from quantum chaos, echoes modern hypotheses about dark matter's potential complexity, and Arrival's heptapods, whose language rewires perception of time, isn't far from how quantum systems might encode information nonlinearly. These stories succeed not by being textbook accurate, but by asking the right questions. What if reality's fabric is stranger than we think? The best sci-fi isn't a documentary, it's a thought experiment. When Interstellar's characters orbit a black hole and return to find decades have passed on Earth, they're experiencing real relativistic time dilation. But the film's emotional core, human connection transcending physics, is where art diverges from equations. Science gives us the rules, storytelling reminds us why they matter. So next time you watch a quantum thriller, enjoy the spectacle, but remember, the truth lurking in the cosmos' coldest corners is dramatic enough on its own. Leading physicists are peering into quantum cold's frontier with a mix of excitement and healthy skepticism, and their predictions read like a roadmap to rewriting physics itself. Nobel laureate Dr. David Wineland envisions ultra-cold quantum sensors in space within the next decade, capable of detecting gravitational waves from the earliest moments after the Big Bang. These devices, chilled to within a billionth of a degree above absolute zero, could spot spacetime ripples too faint for current technology, potentially uncovering echoes of cosmic inflation. Meanwhile, Dr. Junyi's team at GILA predicts the discovery of quantum cooperative phenomena in interstellar clouds, where molecules separated by light years might synchronize their quantum states like a celestial orchestra. Such coordination could explain anomalous energy transfers in cold nebulae, bridging quantum mechanics and thermodynamics in ways textbooks don't yet capture. Not all forecasts are so serene. Dr. Michio Kaku warns of a coming quantum reckoning as experiments push closer to absolute zero. He suspects we'll encounter phenomena that defy our current models, perhaps evidence of extra dimensions or cracks in Einstein's relativity. His boldest claim, that near-zero temperatures might reveal spacetime itself as an emergent property of quantum entanglement, a notion that would upend our understanding of reality's fabric. Supporting this, Dr. Subir Sachdev's simulations at Harvard suggest ultra-cold systems could exhibit quantum memories, where information persists in vacuum fluctuations longer than previously thought possible, like cosmic hard drives preserving data from the universe's infancy. Practical breakthroughs loom too. Dr. Immanuel Bloch anticipates the first quantum refrigerator, a spacecraft-sized device using entangled particles to cool interstellar plasma for study. This could let us recreate the Boomerang Nebula's quantum glow in Earth's labs, testing theories about dark energy's role in photon production. On the theoretical front, Dr. Xiao Gang Wen speculates that the coldest regions of space might harbor topological quantum matter, exotic states where particles remember their paths like cosmic breadcrumbs. Finding such matter could prove space isn't smooth but pixelated at Planck-scale resolutions. Yet dissent spices the discourse. Dr. Sabine Hossenfelder cautions that many quantum-cold hypotheses are untestable with current technology, calling for more modest goals like mapping vacuum fluctuations around neutron stars. Her pragmatic view contrasts with Dr. Andreas Wallraff's optimism about quantum error correction in cold environments, which might enable fault-tolerant quantum computers borrowing tricks from deep space phenomena. The wild card, citizen science. Projects like Quantum Universe are training amateur astronomers to spot cold quantum flares, brief, unexplained emissions from nebulas that professional telescopes might miss. With millions observing nightly, an accidental discovery could accelerate the field overnight. Whatever comes next, one thing's certain: the universe's coldest corners won't give up their secrets quietly. Each prediction, whether cautious or audacious, paints a future where quantum cold isn't just studied, it's harnessed to peel back layers of reality we've yet to imagine. From the frozen depths of the Boomerang Nebula to the ghostly glow of virtual particles flickering in the void, we've journeyed through a cosmos where cold doesn't mean lifeless, it means quantum fireworks. The universe's most frigid corners aren't empty wastelands. They're vibrant theaters where the rules of reality twist into breathtaking new shapes. Who could have imagined that absolute zero, the temperature where all motion should cease, would become a stage for particles that teleport through barriers, light that emerges from nothingness, and quantum connections spanning light years? These aren't just scientific curiosities, they're seismic shifts in how we understand existence itself. Think about what we've uncovered. A vacuum isn't truly empty. Cold amplifies quantum weirdness rather than suppressing it, and even the darkest patches of space hum with hidden energy. The implications ripple far beyond astronomy. These discoveries challenge our most basic assumptions about cause and effect, energy conservation, and the very nature of nothing. They hint at deeper layers of reality waiting to be peeled back, where dark matter might whisper through quantum entanglement, or where the fabric of spacetime itself could emerge from cosmic-scale superpositions. This journey doesn't end here, it's an invitation. Every time you look up at the night sky, remember that those inky black spaces between stars aren't voids. They're alive with quantum potential, brimming with mysteries we've only begun to decipher. Maybe you'll be the one to spot an anomaly in telescope data, or perhaps you'll spark the next groundbreaking theory while gazing at the stars from your backyard. The cosmos rewards curiosity, and there's no greater adventure than unraveling its secrets. If this exploration of quantum cold has left you awestruck, just wait. We've barely scratched the surface of the universe's wonders. From black holes that warp time to dark energy tearing space apart, mind-bending discoveries await in future videos. Hit subscribe to join this cosmic detective story, and let us know in the comments what celestial mystery fascinates you most. The universe has been waiting 14 billion years to share its secrets. Now it's our turn to listen and to marvel at how reality keeps outshining our wildest